Hello, AP students. In our previous lesson, we were discussing the idea of uncertainty of the electron and its position in the atom and its motion. And now what we'd like to do is move into the idea of the chemical behavior of an atom based on its atomic structure from our current quantum day model. Okay, and so in the late 1700s, early 1800s, we had many scientists discovering patterns within the elements that were known at that time. And they tried to create classification systems to help study these elements, and we had many names in the history of the periodic table, like Dobereiner and his idea of triads, meaning three elements in groups with similar chemical behavior. And we had Myers also claiming to have a classification system, but it was Mendeleev who was given the most credit for our current periodic table. And that was because he was able to explain the importance of the table, the idea that we could predict the existence and properties of elements that hadn't yet been discovered. Okay, and so we know that the electrons in the nucleus interact to make the most stable arrangement of atoms possible. Okay, and so we have three basic rules that help us govern the periodic table and its layout. And the first rule is the Aufbau principle. It says that as the protons are added one by one to the nucleus to build up the elements, electrons are similarly added to hydrogen-like orbitals. So what that's really saying in essence is that electrons want to occupy the orbitals of the lowest energy levels first. So they want to fill the s orbitals first, and then they move into the p orbitals, and then the d orbitals, and so on. And so we can show this idea with what's called an electron configuration, because this is basically the arrangement of the electrons in the atom, or the element's address. And so you can see on this slide, it's showing oxygen atom and its arrangement, showing 2 electrons in the 1s orbital, and now that orbital is full. And so now we have 2 electrons in the second energy level, s orbital, and then into the second energy level, p orbital. And then that's all the electrons that oxygen has, and so that would be the oxygen address. Now remember, an orbital can only hold 2 electrons, and each of these electrons has an opposite spin. And this is the Pauli exclusion principle, or the Pauli principle for short. Okay, and then Hund's rule says that the lowest energy configurations for an atom, I don't know why that keeps popping up, the lowest energy configurations for an atom is the one having the maximum number of unpaired electrons allowed by the Pauli principle in a particular set of degenerate same energy orbitals. So what's that really saying? Well, it's saying, in other words, that electrons with the same spin direction are going to be found as far apart from each other as possible. Okay, and then in our next slide here, we can show on orbital diagram notation that also shows how the electrons are laid out within an atom. And it's shown by drawing boxes to represent orbitals, and then arrows to represent electrons, and then up and down arrows to represent this opposite spins. Okay, so I'm going to insert a clip here showing you how to draw these electron configurations and these orbital diagrams. Okay, I'm going to show you how to write the electron configurations, or the address of the elements. Okay, but before I do that,
let's look at this little cheat sheet that shows where overlaps happen in these orbitals because of the idea of energy and stability. Okay, so notice I have all these numbers written out here. All the S's up from period 1 to period 7. All the P's, all the D's, all the F's. Okay? And what you can do is you can use this as a little cheat sheet to get where the electrons are going to change the pattern. So we'd start here with our 1s, okay? And this arrow is representing which numbers you'd write next. And then we go to 2s, and then we go to 2p, and then we see 3s, and then we see 3p, and then we see 4s, and there's our first overlap. And then we're back to 3d, and then 4p again, and then 5s, more overlaps, and then back to 4d, and so on. Okay, and you just keep following this. Just follow the pattern of the arrows. It's kind of like Candyland chutes and ladders. You follow the chute. No, yeah, this would be a chute. Okay, and so let's try one. Let's write the configuration for, let's pick an element. How about if we let's use iron. Okay, so 26 electrons. So remember, we're going to use the cheat sheet here. Okay, so we're going to start out 1s, and then 2s, 2p, and then 3s. Okay, so 1s, and then 2s, and then 2p. And notice s's hold 2 electrons. P orbitals can hold 6. There's 3 orientations in space, each of them holding 2 electrons for 6. And then we go to 3s, 2, okay, and then let's pull this back in front. We hop back to 3p, and then 4s, and then 3d. But I got to count to see where my electrons, where I am at filling my electrons. So we have 3s, and then we have 3p, 6, and then we have 4s, and let's count so far. We've got 10, 16, 17, 18, and then there's 20, but we want to fill 26. So after 4s, we go back to 3d, and d can hold 10 electrons, but we've only got 6 left. And so there we have it. There's the electron configuration for iron, showing the first overlap with the 4s and 3d orbitals overlapping. Okay, and then let me also show you the orbital diagram notation. Okay, another way of showing the address of the electrons, or where the electrons are, but more so a visual of their spin. Okay, and so let's see, let's draw calcium. So calcium has 20 protons, therefore 20 electrons. And so let's see where they are. So 1, 2, 3, 4. See, and I've got an up and a down to represent opposite spins. And each box is an orbital orientation in space. S being spherical, P being dumbbell shaped, having 3 orientations in space. D being kind of clover leafish, having 5 orientations in space. And then if I had drawn F boxes, we would see 7 of those for 7 orientations in space. Okay, and so we're going to keep filling. And according to Hund's rule, the electrons want to be as far apart as they can be when they have the same spin. Okay, so that's why we fill each orbital first, and then we go back and pair them up. Okay, so I've got 2, 4, 6, 8, 10. I'm going for 20 here for calcium, so let's go 1, 2 more. So now I've got 12, 13, 14, 15, 16, 17, 18. Oh, I can't fill here. I've got to fill 4s, 19, and 20. Okay, because the S and the D, remember, they have that overlap. So now if I was writing the orbital diagram for scandium 21, then I'd come back and I'd start filling D. Okay, and so that's a little overview of the orbital diagram notation for where the electrons are within the atom.
Okay, valence electrons now are the electrons that are found doing the bonding. They're the electrons that are involved in the chemical reactions. And so they're really the important electrons for us to pay attention to. And valence electrons are those outermost energy level electrons. And elements in the same group on a periodic table are going to have the same number of valence electrons. Okay? Now we can use what's called a dot diagram to show these valence electrons. And so what I'll do is I'll insert a clip here showing you how to draw the electron dot structure that represents the valence electrons.
Electron dot structures now are a diagram or a pictorial view of the valence electrons that are in the atom of the element. Remember, it's the valence electrons that are involved in the bonding, and so they're the ones that are being transferred during chemical reactions. Okay, so this is how this diagram works. Basically, you just draw the elemental symbol. I'm going to use X for generic symbol. And then you use dots to represent the electrons. Okay? And so it used to be that we'd have one side of the symbol represent S and the other three sides represent P. But then with the idea of the hybridization of S and P orbitals, we end up really kind of changing that pattern. So like our hydrogen element has one valence electron. Okay. Then we go to helium. Helium has two. We can draw it here, or else we could also draw it here. Okay. Now helium really is kind of a special case. And helium we would draw it over here, dot and dot, because helium is a noble gas. Its first energy level is full, so therefore it's not going to do any bonding with other elements. And so this shows that its orbital is filled. Whereas when you draw single dots, you're showing that there's a second position for another electron to come into place, and that's what happens when we are involved in bonding. Okay, so this could represent an element in group 2, really. Okay, because lithium has 3 electrons. The first 2 are in the first energy level, and then the third one is in the second energy level, so it has only 1 valence electron, so we'd have only 1 dot, and so on. And so as we go to fill them, we end up putting 8 dots all the way around. So 1, 2, 3, 4, 5, 6, 7, 8. And it doesn't have to be in that order. Remember, these are representing orbitals, and if there aren't 2 electrons there, that means there's an open spot for an electron to be filled during a bonding situation. So let's just look at the pattern on the periodic table. So I've drawn this out to just show the first 3 periods and the group 1A element, the A group elements. Okay, so group 1 and 2, and then we're skipping our transition elements and we're jumping back into 3 through 8. Okay, and so group 1, they all have 1 valence electron. So they all have this same pattern all the way down. Okay, in group 2, we have 2 valence electrons. And I'm going to show them opposite like this because remember, this is an open spot now and this is an open spot for bonding. Okay, 1, 2, calcium, 1, 2. Okay, now we jump over here to boron. Okay, boron, 1, 2, 3. Aluminum, 1, 2, 3. Gallium. Uh-oh, I have screwed up, haven't I? Look, I'm writing beryllium and boron in this first period. They don't go there. There's nothing here. 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 Nothing here till we get to helium. Okay, so I've made a mistake. Our second energy level, this is where we have beryllium, Be. Let's just scribble that, Be, and then Mg. Okay, and then here's where we have boron, 1, 2, 3, and then aluminum, 1, 2, 3. And then here's where we have group 4, silicon. No, we have carbon, and then silicon. 4 valence electrons. Okay, so they have 4 bonding sites. Okay, and then we go on to nitrogen and phosphorus, and then sulfur and selenium, and then chlorine and bromine, and then our noble gases, neon and argon. Okay, and we continue to follow the pattern. 1, 2, 3, 4, 5. Now nitrogen only has 3 bonding sites. Same for phosphorus. 1, 2, 3, 4, 5. Okay, and then 6. 1, 2, 3, 4, 5, 6. Same thing here. 1, 2, 3, 4, 5, 6. Notice I'm mixing it up because it's just the idea that there's 2 bonding sites. Okay, 1, 2, 3, 4, 5, 6, 7. Change the pattern a little bit, but it's still all the same. 1, 2, 3, 4, 5, 6, 7. Only 1 bonding site. And then our noble gases having 8, so there is no bonding sites. Sorry about that little mix-up there. I wasn't even thinking what I was doing there. Okay, so there's the basic idea of the electron dot structures for just some of the elements in the groups 1A through 8A.
Okay, so in summary, we will have looked at electron configurations, we will have looked at orbital diagrams, we will have looked at valence electrons and their dot structures, and now we can lay out the table, lay out all the orbitals, the s, p, d, and f orbitals, so you can see the blocks that form from the orbitals, and then you can use the periodic table to actually write electron configurations once you recognize the pattern, like groups 1 and 2A are the s orbitals. The D block is the B groups, the transition area of the periodic table. And then we get to the p orbitals, that's your 3A through 8A groupings. And then notice that 4F and 5F get pulled up into the d orbital block. And so the reason they've been pulled out is because it makes the periodic table shorter, not so extended, and it makes it easier to work with. Okay? In the next lesson, we'll look at the periodic trends that take place within the periodic table.